we're almost to the end. So all of you hopefully turned in your project today. This was the actual deadline of the final report. So it will take me a while to grade all of the final reports. But I'll post the grades. After I've graded them. So don't forget you have a poster outline that's due on Wednesday. Okay. And then there's going to be an interim test next Monday. Maybe I'll say a little bit more about that on Wednesday. What'll be an interim? It'll be similar to the midterm. And then let's see. A week from Wednesday will be the deadline for the last homework, the graphs assignment. Just post it. You should have everything you need to do that. Hopefully this is the lightest assignment of the semester. It should be pretty straightforward. And then during your final exam block, right, this is when our final exam is scheduled in the class, we'll do the poster presentations. Okay, so I'll post more details online about this as this will be, but the time is Thursday, April 25th, so a week from this Thursday. It'll be by the SOC so main office, so on the 3rd floor of MEB. That'll roughly be where it's going to be. 3:30 to 5:30 is the official time. If you want to come a little bit early, that'd be great. If I probably will not get through all the posters in 2 hours, I'll try my best. So it probably will be done around 6-ish or so. If you get through, you can leave early if you need to leave before that, or come right at this time. But you should be here for this period of time. Okay.
So there's a question.
Yep.
So is the deadline what's the deadline for the project report at 2:50 today?
So let me look. So the deadline is what it says on Canvas. Okay. So I'm logging in to see that. You do 2-step verification, but if anyone remembers what the Canvas deadline was.
Yeah, today 2:50 p.m. So
yeah. So it was 2:50 p.m. today. That's the deadline I'm going to go by. After that, it's going to be late. Same late policy as the rest of the semester. So okay. So with the posters, so this is kind of the rest of the schedule. Lots of stuff going on. I'm sure all of you have lots of other stuff going on as well. Let me say a little bit more about the posters. So you have to turn in something by Wednesday. This should be an outline, and this should try and be like a full draft of the poster. We want to give you some feedback on this. If you look at the project description, there are two ways so there are two ways to make a poster here. There are two ways to make a poster. If you've never made a poster before and you've made PowerPoint slides and you're really worried about making a poster and you don't want to try something new, it's okay if you make like 12 slides and you print them out and you put them up there. That's not the end of the world. This actually isn't a horrible way to make a poster. It forces some good habits if you have good habits for making slides. However, and if you do that, you're in charge of printing those out yourself to bring them in. We'll provide poster boards, easels, and clips and stuff like that. But you should print out those slides. What most people do, and one thing and this is probably the last year that we'll be able to do this for free, it turns out, but the department will print a poster for you. Okay, but it should be kind of one big poster like these examples up here. And so almost everyone every year does this. This is what I would recommend. It's more fun. You can do more kind of interesting stuff with it. So make one big image. It doesn't matter what program you make it in. It could be PowerPoint or Keynote or like Omnigraph was my favorite. It can be like LaTeX and Beamer, all that's fine. But you need to turn in a single PDF. Okay, the PDF is what we can print. So print it to a PDF or something. If you use, if you have like a non-vectorized format, the PDF will vectorize it. So if it's pixels, it creates a little square for every pixel. So just keep that in mind if you have never made a poster before. Don't go to an intermediate pixelated format if you don't have to. Of course, it ultimately prints essentially pixels, but usually below the level you can see. But that's why a file might be artificially big. So a little of the detail. These will be due. The draft will be due on Wednesday, and then we'll start giving you feedback, right? So Madi is going to go through, and I've kind of given him instruction of giving feedback, and eventually I will review them and give feedback as needed. And the final version, so how this will work is basically he will give you feedback. If he says, you know, this looks good, is this the final version? You can say yes, then we will grab the PDF and we'll put it in a queue to be printed. If we ask for revisions, you need to revise it. It's not final until Madia asks you, is this the final version? I'm okay with this, and you approve. That needs to be done by 9 a.m. Monday, April 22nd. This is the deadline so we can get all 50 posters printed on time by Thursday. Okay, so this will need to start happening soon. Most of you will go through like one round of feedback. Okay, so it shouldn't be too much, but kind of keep in mind, if it doesn't get, you don't send in a final approved printed final version by then, we won't print it for you, and then you may have to go to Kinko's or something else, which Kinko's is expensive. That's why we started doing this. Okay. Okay. So what should posters look like? Okay. Let's go to. So Madia just posted a link to this. This is a PowerPoint template. There's actually like a watermark on here that isn't showing up, right? Which is fine, but this is kind of like a pretty standard way to do it. There are some things I like about it. It's hard to make a really bad poster using this format. 3 columns tends to be good. Have a title easy to see on top with the authors. And it kind of try and break up the different sections into these different kind of parts where they're blocks I can easily follow in the columns. What I'd recommend is in the middle have some kind of cool diagram or image or something that captures people's attention. Okay, and somewhere have some like charts and discussions and plots. So charts and plots that we can describe what the actual results are, right? So think of motivation and data, cool stuff about what you did that catches people's attention, what's interesting, what's new, what's captivating about this, and then something like the results and that can and conclusions. They don't need to be strictly this, this, and this. They can bleed over, but kind of keep them nicely organized. Okay. So most of the posters you see up here do not use this explicit format. There's one up here that does. I can't. There are reasons I'm not supposed to show them because we're videotaping. These are previous students' work, but this is a compromise. So you can come look at these posters after class. I'm fun if you do something even more creative than just doing this. Some of the coolest posters are beyond this, but this gives you a pretty good starting point for a poster. One thing the department has asked since they're printing all these is don't have kind of this background color for no good reason. Like this poster has background color for no apparent, no necessary reason. If it's part of the design and there's some cool kind of design you're doing that integrates that color and coordinates with it, that's fine. But if you don't have like a specific reason, we'd rather not print the color. And then a couple other things I don't like on posters are fonts with serifs on them. Okay, they're little curly things, and they're great for reading documents, but not as good for big presentations. The font on here is probably smaller than I would like. Okay? If you can't read it from where you are, it's probably too small. If you're looking at a computer screen you're making on and you have to squint to read it, font's probably too small. Okay? Don't write paragraphs. No paragraphs. Okay? This is not a poster that... So my view is there are two types of posters in the world. Okay? There are ones that you make the poster, you go put it somewhere, and you walk away. Then someone might need to read a little bit more detailed to figure out what you're doing. The other one is where you make a poster, and the whole time it's up, someone's standing there and can explain it, and the poster is a visual aid to help your explanations. You wish you could write something or draw a picture or show an example to help explain what your project's about. That's exactly what should be on your poster. Okay? So it doesn't need to have a full description. You can say that in words. Right? Yeah, if the text looks like this small, probably someone's not going to sit there and read all of this. If you don't think they're going to read it, then don't put it up on the poster. Okay? That's stuff you can say, and you should know it well enough to say those things. But if you don't think someone's going to read it when they're going to go by and spend 5 minutes or less on the poster with you talking, then you don't need to put it up there. Okay? All right, so any general questions about the posters? All right, so when the actual poster day comes around, I'll say something about this. I'll probably post something on Canvas about this later, but probably you should prepare like a 1 to 2 minute overview that you're going to tell me about the poster, and then I will ask questions for about a minute. And I'll probably move on to the next poster. Okay, so not a lot of time. I'm pretty efficient at these things, but be prepared to have a 1 to 2 minute kind of overview of what you've done. Not a 5-minute overview. That would take me many more hours than I will have to go through all the posters. Okay. Okay. Well, we can say more about that on Monday. There'll also be cool stuff. You'll go look at other people's posters, write results. It's in the project write-up. So you can read about this, and you'll get a handout with instructions on the day when you show up. Okay, so so this will be a lot of fun. And there'll be prizes for in terms of bonus points for the best poster. So all of you will vote on posters. And the people who get the groups that get the most points will get some bonus points. Okay, these are tacked onto your project grade, which is 45% of the class. So 5 points is about almost 2.5 percentage points in the grade, right? So it's worth your effort. Try and make this worth your effort to make a cool poster. And this is voted on by the peers. So this case where I don't have a say in who gets this, so the votes will decide. All right, cool, great. All right, so today we're going to talk about MapReduce and so distributed file systems, which I would like to think of as distributed, so systems for the the masses. Okay, so let's start by saying, how many people here kind of primarily took this class because we're going to talk about MapReduce algorithms? Okay, so I asked this question because around my first few years I taught this class, a third to half the class actually raised their hands. Okay, so it's hard to describe how exciting these ideas of like MapReduce were. So I'll try and give this, and they're still exciting, but they've just become embedded into the culture. What this has done is it's allowed us to scale up data analysis in ways that people thought was not really feasible for most people to do. Working with parallel systems and data that's so big and analysis that needs more than one computer used to be like really, really, really hard to do. Okay, and so when MapReduce was introduced, it was both met with a huge amount of excitement and a massive amount of skepticism at the same time. So I'll try and explain this, give a little bit of a historical perspective here, and I'll say how this kind of connects to all the buzzwords of like the last, say 10 to 4 years ago, not to deep learning, but all the pre-deep learning buzzwords, kind of how they kind of tie into the story. And really what it did is it allowed just about any kind of, any reasonable programmer to kind of scale up their data processing, collection, and so analysis. Throwing away, in some sense, a huge line of research and creating a huge kind of new way of doing things. The poster, all right, yeah, so all that stuff. Okay, good. So this started kind of, one way to think about this was, the starting point was like big data. Okay, so this is one of the buzzwords so I told you we would encounter, and so this kind of came about from my perspective. What big data meant was that we could no longer, like, my research background is like in designing algorithms, and typically an algorithm thinks of, you've got some CPU and you've got some disk and data stored on disk, and maybe there's a cache in here, and so you kind of access data in the CPU, and what your algo does is it's going to look at the number of cycles of the CPU, and it's going to try and design an algorithm that does some operation that counts the number of these cycles of like the CPU. Okay, and so the number of cycles you go through, that's how long it takes to run your algorithm. There's all this infrastructure that allowed you to access data basically in this model called RAM. So like random access memory. Basically, it took one operation to write or read any piece of data to any piece in the memory. And this is not true, but there's this huge stack of things like the multi-level caches and your operating systems and everything, and compiler, which kind of brushes kind of this aside and kind of made it seem like this, where it basically, the true bottleneck was the number of CPU cycles, and you could basically, on average, in most cases, pull one thing from disk or read or write one piece of memory as fast as it took to run through a cycle of the CPU. At least they weren't too far apart, right? But when your data is not even on the same computer, then this started to become a problem. Okay, so what meant to me to like the idea of big data is that data is too big for one computer. Okay, so this meant that I couldn't think of these algorithms anymore. Okay, so like from the algorithm perspective, this is what it meant for big data. You know, there are other views, for instance, like from like the staff's perspective, it means that like the limit is here, so you'd write things like this process will converge in the limit, I get concentration of measure, and you've actually reached the concentration of measure effectively, or at least for more complicated algorithms this was true. So there's other things that happen with the big data revolution, right? But one thing we're going to talk about today is designing scalable algorithms. It no longer fit in one computer, so I can't think of things in like this way anymore. So kind of in the context here that we need to pay attention to is that there are two parts to this. One is, so part one is that the data is, is enormous, let's say on 100 to like 1,000 machines. So it can be even larger than this, but this is kind of a good range to start thinking about this. If it fits on like 5 machines, you might think of a different way of doing this. Think of it in the range of it fits on 100 to 1,000 machines. So you're working on like a data center. Okay, so this is the kind of interesting case to think about. And so the second thing is the data is fairly static. There are going to be some like appends. Okay, so think of you're monitoring some process that's just running, like a simulation, or you're reading off sensors, and there are just logs coming in off these sensors. You're looking at all the customer interactions with like your website, and you're just recording more and more ones as they come. The historical data of what had happened is not changing, right? It happened, right? So that data is fixed. So the data might be doing some updates, but it's almost always exclusively just these appends, okay? And for the most part, you can think of the data as being fixed. You've gathered this huge store of data, and now it's here, and so you can work with this data now. Okay, and so this is the setting. So the data is stored on 1,000 machines, 100 to 1,000 machines, and it's more or less fixed. And so what this has done is this has kind of led to the so the data science revolution. Okay, as I'm going to call this. And so to kind of explain what's going on with data science and why this is going to be interesting is that historically, when you think of so like classic science, so you probably learned about like the scientific method, right? So if you learned the scientific method, right? So this was, so one, you make so a hypothesis, and so it's careful to the way I'm writing down these steps. You go and so you gather data, and so then 3, you check if data supports the hypothesis. Okay, and so basically step 3 is basically, this is roughly like 100 years old. This has really been the ingrained way of doing science. I've got a whole lecture slide deck someplace explaining historically. This goes back to like like Tycho Brahe and like Newton. But kind of for 100 years, this is how we've been running science, very successfully, I should add, up until the last maybe 10 years. Stuff's started to go awry. That was said strangely without the rest of the context of that, which I don't have time for. But stuff's mainly been great with this. I don't have time to explain that statement. It's too okay. So basically, this section 3 is like it's like the field of like statistics is answering this third question, right? So really, I'd say this really became the way to do science around 100 years ago with the development of like statistics. which said, given a fixed set of data that was gathered specifically for this one-time use, how do I assess this data? And it's kind of, and it's important for this to work that this is IID, and it's only used once. Okay, so if this data is used more than once, then kind of some baked-in assumptions in a lot of the statistical theories could kind of break down, and there are a variety of issues with this. And this is what I was alluding to, but kind of the details I'm not going to get into. But this idea of making a hypothesis, you go and gather data specifically for that, and then you check if the data fits this hypothesis, and kind of. Part of this was that if your data did not support your hypothesis, you'd go back and you'd start over again, and you'd gather new data to check over again. You should gather new data on the next step formally. Okay, so what data science is doing is just going to have one step. So it's going to have a step 0, which is usually someone else compute, kind of gather, it's like massive, so pre-compute and try and gather some like massive amounts of data. And then you basically, as a scientist, you just do one step, and that you say, find kind of statistically significant patterns in data. Okay, so and this I would argue is like data mining, right? So in principle, this is what data mining is supposed to be doing. That's not quite how we present it in this class, but you can try and put statistical significance on a variety of these things in certain ways. I'd argue cross-validation does a little bit better job of doing this. Well, I guess we talked about multiple hypothesis testing, right, earlier in the semester? Right, so this is kind of gets into these issues. Okay, so like you have like these Sloan Digital Sky surveys, collect all this data, and now everyone analyzes this, as opposed to an astronomer getting time to look up at one star for a long time. Okay, and that used to be how astronomy worked, and this is kind of the new way how astronomy works, for instance. Okay, so this kind of around a decade, 15 years ago is how science started working, and it means we could pre-compute this massive amount of data, too big to fit on one machine. In order to do data mining, we now need something that works on these distributed stores of massive amounts of data, right? So this is kind of the setting. I mentioned scientific efforts. This was developed, so this led to, like MapReduce kind of came out of here. And this was developed at Google, and they had two main computation tasks that they really needed to do. One was to build the inverted index. So the index so you have a keyword, you map to all the web pages, and you wanted to run PageRank, right? And so these are on this web graph. They're both built with this list of these web graph. That's mainly static. There were some updates to this, but it's for the most part is static. Okay, and they would need to run these big things on this data so big it's not fitting on any one machine. The whole web graph, their whole index. Okay, and so this was a single abstraction that allowed them to do this, but also to look at all their logs data and to do lots of analysis on these logs. So I will go through, we'll explain how it works with these two concepts kind of in this lecture, and a couple of other cases. Okay, so this is where MapReduce came in. So I should add, okay, I want to add in one more thing. So you want to store this data as well. And I think the real innovation here is actually how data was stored. Okay, so the real thing the thing that predated MapReduce by a couple years is, inside Google, this was called the Google file system, and this was a way of way of reorganizing this distributedly stored data. So kind of prior to this, initially scientists kind of wrote down data would write it down in logs and notebooks, and then computers came along, and generally it was really well organized. You put in an Excel spreadsheet or something kind of like that, and there are these kind of classical classical database systems like Oracle database and so forth that is very rigid. Every data point has the same exact columns to it, has the same attributes to it, and there's very little actual, not a lot of missing data in there. Everything kind of looked the same because you gathered it specifically for a task and you recorded exactly those values. Right? Nowadays, data, when you're pre-collecting data, you don't know what's going to be useful, and you store lots of stuff, and everything is kind of different. It's kind of a mess. Right? When you store a web page, what traits on a web page? Oh, this web page does not have a title on it. So where do I put for the title of the web page? Right? Do I leave it blank? And there's all sorts of weird stuff. So they thought of this distributed file system, and the key to this was called a key value pair. And this is kind of now the dominant way of storing data. First, there's XML started this kind of way of thinking about this, and it's the common format now. You can think of the JSON format is the most common way of doing this, and it's a very flexible format. And it doesn't matter exactly what the format is, but it's kind of so everything is stored basically a key, which is going to be some sort of unique, or maybe not exactly unique, but some sort of ID, and it's going to have a value, which is the kind of the raw, so sometimes messy. Data, right? So examples of this would be if you're if you're running some process and you have a log ID. So say I'm running a process and it spits out like an error message or some sort of event happens. I have an ID, and then you have the actual log that's happening. So, for instance, it's going to be error message 42 kind of, and then some specifics about what the state of the machine is at a point like 42. The key could be the web address, and this could be the HTML, or maybe just the outgoing links. So if your goal is just to build something for the web graph, then I have a web page, which is the node, and these are all the edges. I just store a list of edges, outgoing things, or I store the HTML if I want to build something on the index. I need to somehow build something, a function of the HTML. So it could be some sort of document ID, and then it could be the list of the words, or I may have pre-computed this into so maybe the I can vectorize this, or it can be a kgram representation. I can say something about this document. Okay. or I could do something inverted like this. So this would be like the word index or the actual word, and this would be the list of docs with that so word, right? Maybe with extra information, right? So this is the word index. This would be like the inverted index, right? This could be a search term, and this could be the list of the documents, maybe with ranked order that contain this word. I might want to return. Okay, so this might not look like a database, but this is kind of effectively an unstructured database, or very loosely structured, this key value pair. Okay, and so this was kind of the rough format of what's going on. Now, the distributed file system took this key value pair and it stored it kind of in kind of a thoughtful way, but very different than how we had thought about storing things. Okay, it stores things. Data was in these blocks. Okay, and so blocks could change values, but think of a block equals to say 64 megabytes. Okay, so there are lots of the files I described could be fit in like 64 for megabytes. And you can fit several files in this block. So several files which are hopefully similar to each other. Maybe they were created in order, but then if I want to store things which are similar, I can fit several of them inside this block. You could change the block size if that's not the right size for the sort of data you have, but this is kind of the standard way of like setting it. And then each block is stored two or three times. Okay, so I don't store each block once, but I have 2 or 3 copies of every block. And so I'm blowing up my space somewhat, but space is cheap enough. I probably, if I have a data I'm analyzing, I'm probably going to make some copies of different parts of it anyways, so this usually isn't a problem. And then I kind of, I get rid of locality. Okay, so this is what's kind of interesting. I'm going to not try and store nearby blocks next to each other. I'm not going to store copies next to each other. I'm going to try and store related blocks, things that occur. If I have a list of them in some order that they came in, those neighboring things should be on like different computers, right? So if I have, let's say I've got a list of computers here, 1, 2, 3, up to say 999,000. What's going to happen is I'm going to get these blocks coming in. My data is going to come in and to chunk it up into these blocks. And so this one is going to be sent to 2 or 3 different locations. And the neighboring one will be sent to these locations which are going to be different. I'm not going to put them necessarily in the same cell, in the same machine. They can be, these are the different computers. They don't need, it doesn't matter if they're right next to each other or not. But I'm basically going to store these at random essentially. Okay. This was kind of the interesting innovation what's going on here, having this flexible format where all I know about is usually I will first process stuff by just looking at the ID, the key, and the key value pair, and then all the messy stuff is going to be in the value part. So it's a very flexible format. I have roughly these uniform size, roughly 64 megabytes blocks. I make 2 or 3 copies of them, and then I distribute these blocks. Okay, so this gives me a lot of flexibility, and the real advantage of this is that it's very So resilience. Which is that spelling right? So say to like machine like failure. Only one O. Okay, good. So what would happen is that if you have like 1,000 machines, within a week or within a day, probably one of these machines is like going to crash. Okay, just something weird will happen. One will crash. If you have a long process that's running on the order of a day and it crashes, then you don't want to have to restart this whole process. As the number of machines scales up, the probability of at least one machine crashing also goes up. Right? So I have to be resilient to machines crashing. There's this cool graphic that like when Google was advertising this stuff that they had, that the kind of the standard way of doing these parallel algorithms was you bought this one really expensive, powerful machine that had really fast cores, really integrated memory. You could put lots of little like slats in these, like this mini supercomputer that you would buy. And for the amount of memory and computational power, if you just added it up, it was like super expensive. But it was guaranteed not to crash as often. It would be much more resilient to failure. Maybe 1/10 the time if I just bought some off-the-rack kind of like computers from Dell or something like that. And so if those would crash much more often, but the cost was much, much cheaper for the same storage and the same computational cost. Okay, and so if you can be resilient to failure of a few machines, then that was a much better bargain. And so Google kind of, they figured this out. Actually, you know, the company started in like the grad students' dorm room or office, and they just gathered everyone's old machines, and they were just running these machines, and they would fail all the time. But they kind of, you know, this was a formalized later on, but they were very familiar with this. Things can fail all the time. I don't want this to stop the whole operation. So this was extremely like resilient to failure. And so this is how most data is stored now in these large distributed systems. This was not generally the case before this. And so this has really lasted, this distributed file system concept. MapReduce, as I'll describe next, has kind of been, there's more specialized and more tuned things that have come along and effectively have replaced it. The concepts are still there, and I'll teach those. But these distributed file systems are the way to store these massive amounts of data now. Okay, so finally, we can talk about, so like, what is MapReduce? All right, so kind of the MapReduce came about because distributed programming was very hard. You have to worry about these, you cannot guarantee you have these atomic operations anymore. If I send a message, I may need to wait for a while. There's these race conditions. And it was painful. And so what they kind of realized was that you can kind of write down this fairly simple paradigm, and which involved a map step and a reduce step. And you can program most interesting things in this paradigm, especially if it's a distributed file system with the key value stored. Okay? And so this went against a lot of research that said the optimal way to do this is this or that or this, and we've developed all these systems, and they said, no, this is just simpler, and it works. And so there's a lot of pushback, but also this kind of made parallel distributed computing possible for like the masses. Anyone could program this sort of stuff. Maybe not efficiently initially, but we'll discuss some of these issues. All right, so the data, so this, there are going to be 3 steps of this: the map, and the reduce step. Okay, and there's going to be a step in between, but you only have to program these two steps. There's an underlying system which takes care of everything else before you. Okay, and so this is going to read blocks from the key value store. Okay, it's going to read them, and it's going to essentially pull out kind of important info. Okay, so conceptually what it's doing is going to read through these blocks, it read through all the key value pairs, pull out the important, the important info, and determine kind of the new, let me say it like this, the new locality. So I want to identify what property do I want to group certain blocks together by? Or do I want to do analysis? Say I'm doing something like clustering. 2 points near that should be nearby in a cluster, should be somehow local to each other, so I can do some low-level comparisons. Right. So determine some sort of new locality. I'll describe this in more detail, but let me give the conceptual overhead. Then there was this like shuffle step, and this was done by the system, and so this kind of is going to, what this is doing is going to identify like a new key, and this is going to group by this key. Okay, so it's going to take, I'm running through these blocks, I'm outputting these new key value pairs, which are going to be mapped to new blocks, and the ones with the same key should be on the same block. So basically, same key is going to be the same new block. Okay? So the data is on one set of computers in one blocks. It's going to ship them, think of a new set of computers in new blocks. They could be the same, they're probably the same computers, but there's no kind of meaning this computer is the same as that computer. So think of just a new set of computers here. So think of, I've got computers here. I'm going to run some sort of map step here, and that's going to send data out to this new set of computers, and then I'm going to do a reduce step afterwards, and this mapping, this kind of moving from one computer onto the next, internally, this is going to be like the shuffle. And so the key thing is that if there was some particular key, let's say key here on both these two initial computers, the same blocks, then they're going to end up on the same block over here. Right? So both of those are going to map onto the same block. So I'm going to group by the same key. Okay, and this is going to give me a new locality so I can compare everything that has some trait. Or I can count something that has some trait. Okay, and then kind of this. So then this final reduce step is going to look at all key value pairs with the same new key and do a post process. Right, this post process would be something like the analysis. Okay, so this is where the data analysis would occur. The mapping step determines what part I should determine similar objects are. I want to compare these things together, and then the reduce does the comparison. The shuffle does all the distributed computing stuff in between. Okay, so the shuffle takes care of that for me. Yes?
3 letters, go and group these together. If you have 2 letters, group these 2 together. Or how do you do matching by key?
Yeah, so think of all, okay, so the kind of, how about I go through the first example and hopefully it'll be clear, right? So this is like the hello world of like MapReduce, okay? So the problem is the word count. I have, so I've got input all of the English like Wikipedia, and it's broken into these blocks, right? Articles, they're articles grouped together into a similar block. I'm going to read one block at a time. I want to know how many times does each word occur, okay? So, so I'm going to break this into, so might be too big. There's bigger data sets like this, but think of a bigger data set that needs to be stored on multiple machines. How do I count each word? And so the map phase is going to go from a doc to a series of, so that it has a doc ID to a word and the ID. So this is the word, you know, or it word ID was, say, and then like good, okay, right? And if this doc ID was the 7 doc, then I could put like a 7 here for all of them. Okay, right? The other thing I could do is, so I just want the count. I don't need the ID. I can just put a count. This is a 1. So the number of times it occurs, I saw it was good is the text. It occurred once, was occurred once, good occurred once. So I have a count. Okay? Okay, and then what the, you know, the shuffle step groups all the instances of the word good onto the same machine. The shuffle does that for me automatically. A little bit more space, okay. So the shuffle is doing that almost like automatically. So the input here is going to be a set of, say, good 1, good 1, you know, good 1, right? So this is the input to set a bunch of the same word good and the number of times it occurs, which is 1, and the output here is going to be good, which is the word, and the sum of all of these values. All right, so I'm just taking a sum of all the values. So this would be, say, V1, V2, up to Vn. Right? And I just take the sum, and this is the word count. Right? So pretty simple, right? So I have this huge data set distributed on machines. I want to do the word count. I need to kind of do this simple parsing, and I need to just take a sum. That's all I need to write the code for. So the code is just a couple lines. The shuffle step behind the scenes handles all of the distributed issues for me. So that was kind of the magic of it. And this scales up as much as you want. If a machine goes down, it knows that, okay, I sent something to a bad machine. I need to go and look up my backup, my resilient block in case that one went down, and I can carry on with the operation. Right? The whole MapReduce backend wrote all the distributed systems parts, so you just need to write these 2 steps. Okay. They didn't invent these 2 steps. This is from like the programming language community has kind of said, these are 2 really good steps you can do a lot with. They just said, let's implement these 2. And this made a lot of sense. Okay, so this is all you need to do, except it isn't. There's a problem with this. Okay? So what if the input was the word like the? What's the problem going to be? right? So it's known kind of like statistically in English language. I don't know exactly for Wikipedia, but the word the occurs like 7% of all words. Okay, so if the idea was I have 1,000 computers, each one should have roughly 1/1000th of the work, this is forcing 7% of the data onto one machine, which is not what I want, right? So this one is going to be the last to finish. It probably runs out of space. There's several issues, right? So one issue is I can kind of, well, I map it onto a couple of machines. I add those up and I do that. Or I just wait for this machine to finish. I can do this in a streaming fashion. There's actually another step, another thing I can do, and I can have let me see if I can, I put this too high. Okay, great. That was cool. Okay, so there's actually a 1.5 step called, in my mind I thought it was 2.5, so I left the space in the wrong spot. Okay, so there's this combined step, which is optional, which you can do. So think of the map step as reading in a stream. I read over it once, I spit out tokens, these key value pairs. For every word I read, I spit out one of these key value pairs. What the combined step is, I can basically merge these key value pairs before so the shuffle. Okay. But instead of having just a streaming MapReduce, when I'm done with a computer, before I call the shuffle phase, what I'm going to do is I'm going to kind of aggregate or do some post-processing to it to hopefully reduce the amount of storage or the amount of communication costs. Okay, the big bottleneck here are the number of red edges here is the communication between the nodes, typically, right? So if I can reduce that, then this is going to be better. Okay, so if we go back to our example, I want to add in a like combined step. What would I do here for a combined step? So I'm going to get these word and the value word and the value 2. And what the combine is going to do is it's going to give me a single word, like the word good, and just this sum of all these values. So it's the same step as down here, actually. Right? So I'm doing a combine before I do the shuffle. And so what it means is that instead of just one, I'm going to have something like this might be 1, this might be 3, this might be 2. So for certain documents that use the word good more, well, I just have a larger counter, and then I can just do the sum here, right? So it's as long as your operations you can compose them this way, then you can do this, and this will save lots of communication, and it will greatly reduce this. It still probably is. Every single document is going to probably have the word the, at least every English language document. But the counts are not going to be, but I'm not every instance of the word the am I going to have to do this. So I probably can reduce this down to less than 1/1000th of kind of the size of the original data set. Okay, and this will then probably make this work. Okay. So good. Okay, so I want to say one more. I'm going to go through some more examples, but let me say one more thing about the general algorithm first. So you can chain these together. So sometimes, like with the word count, I just need to run one map, a shuffle implicitly, and then do a reduce, and I'm done. Okay, but sometimes I need to kind of I can't do this in one step. And so most of the cost is actually in the shuffle step, and the reason for this is that in order to allow you to recover from a crash, every time it does a map and a reduce, is it rewrites the output of the reduce back onto disk. Okay, Okay, you can imagine this is going to be fairly slow. And there's some like other stuff with the Java. There's like in MapReduce, or at least in the Hadoop implementation, which is the open access, the open source version of this. There's some Java kind of virtual machine like restarts or something like this. And so this is pretty slow to do one round. And that even if the total time of sending the data to in between the machines is, even if it's a small amount of data that needs to be sent, it writes it back to disk and then restarts the process again and maybe re-queues up a new process. There might be multiple kind of MapReduce kind of jobs trying to run on the same cluster. So this kind of really slows things down. So people try and design things at small amount of like round complexity. I want to do the smallest number of maps and reduce in order to do a more complex task. Can I get this to be small? So even something like a log n steps, if I have a billion data items, that might be like 20 or 30 steps, log base 2n of that, and that might be too big. The log base, a block size, where the block is a base size, block size, is probably a small constant like 4, and that might be okay. Okay, so this kind of gets into the more advanced design of these algorithms. There are these newer systems, not even that new anymore, but called, like there's a system called Spark. So it's like an Apache project. And this has really reduced the cost of a single round. In my view, that was the big kind of gain from doing Spark, is that it has all the same resilience. It's a little bit harder to program. You have to have these resilient data structures. But these RDDs, they call them, but the round complexity is really cut down. So if data only needs to move fairly, if there's some like local structure coherence among the machines, among the data, you can take advantage of that, and the round complexity goes down. You don't need to write back to disk entirely every time. So that's kind of the major innovation with Spark. And if you can do it, I would try and look into that instead of Hadoop. Hadoop might be still a little bit easier to interface, but it's not drastically so. Okay, so let's just go through some more examples. That's what we'll do the rest of the time. Okay, so I promised you that one of the main things, one of the big computational workloads of Google at the time was building this inverted index. And this basically, for every web page on Wikipedia, let's say I want to build a search engine over this. So for every word I search for a word, I want a list of all the Wikipedia articles that are containing this word. Right? So we can sort them later, that's fine, based on some kind of PageRank sort of criteria. We can talk about PageRank in a second, but let's just, for every word, give me a list of all the pages it's on, where data starts as I have just all the pages that contain the words. Okay, so for map, how do I do this? I have a, let's call it an article, and the output here is going to be, let's call this ID, as an article ID, and I'm going to have a word 1 ID, word 2 ID, and so on. Right? So I'm just, for every word I see, I create these tokens, and then in the reduce, I'm going to have for each, I'm going to have some word I, right, the ith word, and then I'm going to have the page ID 1, word I, this same word, ID 2, and so on. And basically the output here is going to be a single key value pair with the word and the union over I of all these, I guess, let's do index J. So word I and the union of all of these IDs. Right, so now just instead of the sum, I just collect the union. I just need to write some sort of something that accumulates them into some set data structure. Right, so again, as a programmer, you just need to write a few lines of code to parse this and then to throw them into a data structure. Everything else is done for you. Right, so super simple. And if I have a word occurs a bunch, I can add in this combiner step as well, because this union is mergeable. I can compose these operations. Okay? I can also, let's say, I want to also get some, I want to do some other information. Let's say I want to do the 3 grams instead of the words. Right, and I want to know if there's a sequence of 3 consecutive words which appears on a page. Right, so this is basically not much harder than before. In the map phase, I go from a document ID, and I'm going to output, say, word 1, word 2, word 3, ID, word 2, word 3, word 4, ID, and so on and so forth. So instead of just looking at each individual word, I create these shingles of 3 consecutive words, and then on a reduce, the input is going to be word I, word I prime, and word I prime prime, which is a sequence of 3 words, and I'm going to have some ID 1. I'm going to have the same 3 words, word I prime, and word I prime prime, and ID 2, right? And the output is the same as before, word I prime, and word I prime prime, and just the union over J of ID J, right? So just as simple. So I can do something slightly more complex in the processing to build other search terms as well. I can also do other statistics on the HTML, I want to say all the outgoing text, all the outgoing links, like find all the pages that link into one page. It's just slightly different on the map step. I determine what is important here, and then I aggregate them or do some simple post-processing in the reduce step. And the shuffle takes care of everything else for me. Okay? Okay, so here's another algorithm that I wanted to mention. I figured I should mention this in the class. We haven't seen this in class before, but this is kind of a pretty, I think a pretty important algorithm that kind of sits between data mining and machine learning, what we teach. So, so this is called label propagation on a graph. Okay, and the idea is that I've got some input graph, and it has these edges, right? And I may have, okay, and so some of these have labels on them, like this one is going to be plus, and this one is plus, and this one is minus, and this one is minus. And so, but not all of them are labeled, right? So I have some labeled data, so this is called a like semi-supervised problem where I have some labels, and I want to predict the labels on the unlabeled ones. Okay, this could be values as well, but for classification, it's just a little bit simpler. I want to predict the label on these other ones. And so what I basically want to do is I want to look at certain of these vertices, and I want to say, well, what label would I predict on here? And I say, well, this one, I don't know what the label is, but this one is a plus, and this one is a plus. And so I'm going to assign, I'm going to be confident enough to kind of fill this one as a plus. And similarly, maybe I'm going to, yeah, the other ones I probably couldn't make a guess on. And then maybe there's some on the boundary I don't know. Maybe at the end I vote or something like that. Okay, but this algorithm works extremely well in practice if you have a good graph. If I have some values on nodes, I want to propagate those to ones where I can basically, if I'll set some threshold, let's say I have at least 5 labeled neighbors, and if I have a node which is unlabeled, I have at least some number of labeled neighbors. In this example, I use 2, but it could be, say, 5. And then I will take the majority vote of those neighbors. Or maybe I'll only assign it if it's at least 4 out of 5. At least 80% of them are one way or the other. Okay, so how would I run one round of this label propagation if the data is stored as nodes and it has the edges on those and possibly a label?
So is your ID kind of like the node ID?
Yeah, right. So think of the initial, at the map step, the ID is the key is the node ID initially. And initially it's going to have this node, or this node will have a list of edges and will potentially have a label, or it'll say no label. So if my input, this is the input, I'm going to, let's say I'm this node right here, I'm going to have a plus as my label, and I'll have E1, E2, EK. And this edge basically is going to be point to, like this is going to be another node ID. Okay, so what I'm going to do is this particular thing is going to output E1, which is another node ID, and it's going to give its label. E2, its label, which is this guy right here. Okay, so for all of its edges, it's going to send out its label. Okay, for the ones, and I only do that, I say, if the label is not equal to the empty set. If I don't have an unlabeled thing, then I create all this output. If I'm sitting at one of these nodes, I don't have a label, I don't have anything to send out. I don't propagate my labels. Okay, and so then in this reduce step, right? I'm going to have some ID, and I'm going to have label 1. I'm going to have the same ID, label 2, right? And I probably also need to send out always and also ID plus, say, and then some special tag, say, that's fixed. Right? So I'm going to say if no fixed tag, right? So if I would send this, so these will get aggregated. So if I'm sitting here, I might try and get a label sent from over there, but I know this one's fixed. So if I have the special tag says it's fixed, I don't do anything. So if no fixed tag, then then I'm going to say if the kind of the number of label is greater than 5, then output ID and the majority of this label 1, label 2, and so forth. That's been sent out here, right? So if it is fixed, then I just output the original label. I keep the original label. If it's not fixed and the number of labels greater than 5, because I can run a counting process, simple, just like word count, then I take the majority of all these things and I assign this as the new label, and this is one round of label propagation. I can then run another round of label propagation. Usually you run a few rounds and this gives you labels lots of your data. Okay, right, so this was pretty easy. Slightly more challenging. I'll just mention it without writing this out because I want to get to the next one as well. Let's say instead, and this is another kind of variant of this algorithm, is say you have an embedding. I've got a data set X, and it's in some d-dimensional space, and I have a subset of the points X prime with these labels, positive and negative, and this implicitly will define a nearest neighbor graph. Let's say implicitly finds a graph, let's say the 20 nearest neighbors, or maybe I can say the neighbors are within some sort of threshold. What would be a way of doing this now? This seems, I don't have an explicitly defined graph anymore. And maybe I'm willing to approximate the notion of neighborhood. So I'll just say, so I can move on to just mention how to do PageRank in this model. I can do this using LSH, and it's simple in 2 rounds. And I'll let you think about that a little bit. Okay? You might be able to do it in 1 round. I haven't thought enough about it, but you can do it in 2 rounds with LSH. Right? I can define some hash function based on some threshold I want. And so if it satisfies a hash function, then I send this node off to some neighborhood. And then I have to take an OR, so that's why I need have to do the second round. I'm going to have multiple tables, and if it collides in any table, it might be a nearest neighbor. So I need to do an OR, and that might take a second round. Okay, but you can think about the details. It's still not too hard, right? The LSH, the hash functions are not too hard to do. Taking an X round with an OR would probably be not too hard. Can you do this in 1 round? Okay. So let's say a little bit about PageRank. If you remember, the PageRank goal is to create essentially, well, it's to create Q star equals P star times Q0, right? And so let's say I've got a warm start, and I can actually, basically, I'm going to approximate this as P P times P times P. Right, so I'm going to call Q0 to a vector matrix multiply on P, and this would be an example of I can use M up there, and then I take this output, multiply it by another one here, and I'm going to do this some number of times. Okay, so each one of this matvec operation is going to be 1 round of MapReduce. And then I'm going to do something like usually less than 50 rounds. Okay, so there's some bounded number of rounds I need to do. This would be maybe more expensive. If I have a good warm start for Q0, maybe I just need to do 3 or 4 rounds of this. Okay, 50 rounds is probably not a lot to do every night, but I do this once at the beginning to seed the PageRank vector, and then every night I maybe do 2 or 3 rounds to kind of update this. Okay, but the big step is I have to do this huge matrix vector operation. I've got this huge matrix that's describing this web graph, and it's very sparse, but Q0 is dense. So this is huge. So the matrix is the data essentially, and that means that's distributed, right? And so this is going to be one web page. And so the kind of classic way of thinking about it is that some set of web pages is going to be one block. Okay? So I'll group web pages together into these blocks, right? And so I can store them sparsely. Like each web page, I actually just need to store the outgoing links just in a list. I don't want to actually store all the zeros. Okay? And so, and just to simplify, think of each web page as one of these blocks, just because I have a small example up here. Right? And so what happens is you can think of having Q1, it's Q of 1, Q of 2, Q of 3, Q of 4 in these columns. And basically what happens is the first entry of this Q matrix, my PageRank vector I'm updating, I multiply it by this column and I send, and it sends its contribution to this new web page here, and this creates this is a new ID, and this is Q1 times 1/3. Okay, so this outputs one ID, and then I need to add these all up. Right, so this is processing this one web page. It creates, for every outgoing link, it creates some contribution there, and then I need to add up all these contributions inside the reduce step, and that gives me one step of this. There could be cases where it's better to actually block things this way. The problem is you have to you have a lot of different outputs from every web page. If a web page has a lot of outgoing links, it's going to create lots of these things, and I can't use a combiner on them. So if I have a lot of web pages with a huge number of outgoing links, this is actually going to cause a problem and may cause a page to overflow, a block to overflow. So it might be better to block up some of the web pages like this instead, and you can instead, the input to one of them is a few numbers instead of just a single number, and then but the output can be aggregated then. And so for really, really large things, and as the matrix gets denser into maybe some other matrix vector operations I might want to do, then blocking this way is sometimes a little bit better. Okay, great. So I'll stop there. Great. Remember to send your poster drafts in, and then we'll have the final lecture on Wednesday on more stuff on graph analysis.